In 1963, Stanislaw Ulam was sitting in a long, boring scientific lecture. He needed something to do with his hands. He started doodling on a piece of paper. He wrote down the positive integers, 1 in the center, 2 to the right, 3 above the 2, 4 to the left of the 3, then 5, 6, 7, 8, spiraling outward, counterclockwise in a square, each circuit a little larger than the last. Then he marked the primes, 2, 3, 5, 7, 11, 13. He blackened those squares. The blackened squares didn't scatter randomly. They lined up, in long, clear, parallel diagonals, streaks of primes appearing along straight lines across the grid. Ulam looked at his doodle, looked again, and realized he was looking at something nobody had ever drawn before. He showed it to his colleagues at Los Alamos. Within a year, Martin Gardner wrote about it in Scientific American. The image went on the cover in March 1964. Within a decade, it was in every recreational mathematics book in print. Ulam never wrote a research paper on it. He just doodled it, showed his friends, and went back to physics. He was a Hungarian-American mathematician at Los Alamos. He had helped design the hydrogen bomb. The Ulam spiral was, for him, a 15-minute afterthought. But the diagonals are real. They are not artifacts of the rectangular layout. They show up in every variant of the spiral. They reveal something deep about the distribution of prime numbers, something we still do not fully understand 60 years later. To build the spiral, you start with 1 in the center of a grid. 2 goes immediately to the right, 3 goes above the 2, 4 goes to the left of the 3, 5 goes to the left of the 4, 6 goes below the 5, 7 below the 6, 8 to the right of the 7, 9 to the right of the 8. Now you're back below the original 2, ready to start a new circuit. Each circuit is 2 squares wider than the last. Circuit 1 held the integer 1. Circuit 2 held 2 through 9. Circuit 3 holds 10 through 25. Then 26 through 49. Then 50 through 81. The corners of the nth circuit hold consecutive squares. 1, 4, 9, 16, 25, 36, 49. That's the layout. Then you mark the primes. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. If primes were distributed at random, and there is no obvious reason they shouldn't be, you would see a uniform speckling. A speckling, but no pattern. Diagonal coincidences are possible by chance, but should not persist as you go further out. They should average out and disappear. But they don't average out, they persist. Some diagonals stay extremely dense in primes for thousands of cells. Others stay extremely sparse. There are bright streaks and dark streaks, and the streaks line up along exact diagonal directions of the grid. The longer you draw the spiral, the more obvious the pattern becomes. At 1,000,000 integers, the diagonals span the whole image. At 1,000,000,000 integers, which has been done, they're unmistakable. The Ulam spiral is one of the most reliably reproducible visual patterns in mathematics. Why diagonals? Here is the mathematics. When you walk along a diagonal of the Ulam spiral, the integers you land on follow a quadratic progression. Take a step along the main diagonal, the southwest to northeast direction, and you go from n to roughly n plus the local circuit width, which is itself growing linearly with the radius. The result is that consecutive cells along a diagonal differ by a value that grows linearly. So the integers along a diagonal are the values of a quadratic polynomial in one variable. To make this precise, label the cells by their position on the diagonal. The integer in cell k along a particular diagonal is given by something like 4k squared plus 2k plus a constant, or 4k squared minus 4k plus an offset. The exact form depends on which diagonal you pick and where you start, but every diagonal is of the form ak squared plus bk plus c for some specific integers a, b, c. This means a diagonal that contains many primes is a quadratic polynomial that takes many prime values. A diagonal that's empty is a polynomial that mostly factors. The question of which diagonals are prime-rich becomes the question, which quadratic polynomials take prime values often? This is a question with a known partial answer. Some quadratics, due to their algebraic structure, cannot take many prime values. For instance, any polynomial that factors over the integers n squared minus 1 is n minus 1 times n plus 1 only takes prime values when one factor is plus or minus 1. So n squared minus 1 is prime almost never. The interesting quadratics are the irreducible ones, the ones that don't factor. And among those, some appear to take prime values astonishingly often. In 1772, 200 years before Ulam, Leonhard Euler noticed an extraordinary quadratic. F of n equals n squared plus n plus 41. Plug in n equals 0, you get 41. Prime. Plug in 1, 43. Prime. Plug in 2, 47. Prime. Plug in 3, 53. Prime. Plug in 4, 61. Prime. It keeps going. 61, 71, 83, 97, 113, 131, 151. Every value from n equals 0 up through n equals 39 is prime. 40 primes in a row. At n equals 40, Euler's polynomial gives 1681, which factors as 41 times 41. The first composite. After that, primes thin out. But Euler's polynomial continues to produce primes at an unusually high rate, far higher than a random quadratic of that size should. In the Ulam spiral, Euler's polynomial appears as a particularly bright diagonal. Every prime it produces shows up as a marked cell on that line. The diagonal is unmistakable in the lower left quadrant. Why is 41 special? The answer involves deep number theory. Euler's polynomial is connected to the imaginary quadratic field Q of square root minus 163, the largest of 9 special imaginary quadratic fields with unique factorization. The discriminant of Euler's polynomial is minus 163, the same 163 that makes e to the pi times square root of 163 nearly an integer. This is one of the deep coincidences. The prime richness of n squared plus n plus 41, the failure of e to the pi square root 163 to be transcendently far from an integer, and the existence of the imaginary quadratic field with discriminant minus 163. They are all the same fact, written 3 different ways. Ulam noticed that Euler's polynomial wasn't the only one. Many quadratic polynomials are prime rich. The polynomial n squared plus n plus 17 gives 16 primes in a row, starting from n equals 0. The polynomial 2n squared plus 29 gives 29 primes for n from 0 to 28. The polynomial n squared minus 79n plus 1601 gives 80 consecutive primes for n from 0 to 79. That's the current record for a polynomial with leading coefficient 1. For each of these, there is a Heegner-style explanation. The discriminant of the polynomial corresponds to an imaginary quadratic field with small class number. The smaller the class number, the more primes the polynomial produces. But beyond these specific record holders, there is a more general statement. The hardy Littlewood F conjecture, from 1923, predicts the asymptotic count of primes generated by any irreducible quadratic polynomial. For f of n equals an squared plus bn plus c, the count of primes f of n with n less than capital N is conjectured to be c of f times square root of n over log of n, where c of f is a constant computed from the discriminant. For Euler's polynomial, c of 41 is large, around 3.32. For a generic quadratic, c is small, around 1. So Euler's polynomial generates over 3 times as many primes per unit length as average. The conjecture has been verified numerically up to enormous bounds. The fit is excellent. But the conjecture itself, that any irreducible quadratic produces infinitely many primes, is unproven. We don't even know whether n squared plus 1 is prime for infinitely many n. We can predict the answer to high precision. We cannot prove it. In 1994, Robert Sachs wondered, What if the spiral was different? Sachs rearranged the integers to follow an Archimedean spiral, where the radial distance from the center grows as the square root of the integer. The cells are no longer arranged on a rectangular grid. They are points on a smooth curve, equally spaced along the curve. In this layout, the perfect squares 1, 4, 9, 16, 25 all line up along a single ray pointing outward from the center. They form a straight radial line. So do other quadratic sequences. When you mark the primes in the Sachs spiral, the diagonals from Ulam's version become spirals, or rays. The Euler polynomial primes still cluster along one specific curve. The pattern hasn't gone away. The geometry has changed, but the prime richness of certain quadratics is invariant. Other variants exist. The Kleber triangle arranges the integers in a triangular spiral, Pegg's triangular array. The Gilbert spiral. Each layout reveals the same underlying truth in a slightly different geometric form. The mathematics doesn't care about the layout. Prime richness of quadratic polynomials is an intrinsic property of the integers, not of any drawing. The Ulam spiral made it visible. Sachs and others made it more visible. But the underlying fact that certain irreducible quadratics over the integers concentrate primes at rates conjectured by Hardy and Littlewood is independent of how you draw it. The takeaway: visual coincidences in mathematics often hide structural truths. Ulam, with no theoretical setup, drew a picture and discovered a structure that mathematicians had been studying for 2 centuries without seeing it laid out in front of them. Skeptics asked, are these diagonals real or just a visual coincidence? The answer is both. The diagonals themselves are real. They correspond to real quadratic polynomials, which really are prime-rich in the rigorous sense. The visual impression of streaks is faithful to the underlying mathematics. But the relative brightness of any specific diagonal can be misleading. The eye exaggerates. A diagonal with 30% more primes than average looks 5 times brighter than a uniform background. The visual impact is amplified by the very small density of primes among integers. At any given scale, you're seeing a fraction of about 1 over log n of the cells lit up. Adding 20% more primes to that fraction looks dramatic. A careful statistical analysis shows, yes, the diagonals are statistically significant. The number of primes along certain diagonal strips exceeds chance by a substantial margin. The Hardy-Littlewood F conjecture predicts the size of these excesses, and experimentally, the predictions match. The deepest open question is whether any specific quadratic polynomial generates infinitely many primes. We believe yes. We've checked Euler's polynomial up to n equals 10 to the 12 and still find primes at the predicted density. But proving it is open. It would imply, as a special case, the irreducibility of certain Galois groups and the non-vanishing of certain L functions at 1. So the Ulam spiral is a visualization of a deep open conjecture. Every diagonal you see is a polynomial whose density of primes is predicted but not proven. The image is true. The asymptotic explanation is conjectured. The verification that the polynomial really generates infinitely many primes is still beyond what mathematicians can do. Stanislaw Ulam died in 1984. He never wrote a research paper about the spiral. He didn't think of it as a research contribution. It was a visual curiosity that he showed to his friends. In his memoir, Adventures of a Mathematician, he mentions the spiral in passing. A single sentence, almost an aside. He says he noticed it during a particularly tedious lecture and was struck by the patterns. He doesn't claim anything more. Yet in the 60 years since, the spiral has become one of the most reproduced images in popular mathematics. It appears in textbooks, on posters, in art installations. It generates large-scale prints, computational artworks, screensavers. People generate it to 1 million integers, to 1 billion. Each version looks the same. The diagonals are stubbornly present. What did Ulam see exactly? He saw the visual signature of the Hardy-Littlewood F conjecture, 200 years before anyone had given it a name. He saw the structure of prime-rich quadratic polynomials in raw graphical form. He saw something that, in retrospect, mathematicians had been calculating about for centuries, without ever drawing. The lesson is general. Mathematics has structures that are easier to see than to formalize. Sometimes the visualization comes first, and the theory comes later. The Ulam spiral isn't a theorem. It isn't even a conjecture. It's a picture of a conjecture, and the picture is striking enough that mathematicians ran experiments on it, calibrated the F conjecture against it, and now use it as a teaching tool for an entire branch of analytic number theory. Ulam doodled for 15 minutes during a lecture. He saw something nobody had seen. Sometimes that's all it takes.